When they say there's an energy crisis, it rings false to me. In fact, I find it aggravating because a crisis of supply of energy is physically impossible. Literally, according to physics, everything is energy. So an energy crisis is imaginary. It's made up. Energy is dripping from the walls in nature, and in nature, the walls are made of energy too. Energy is, any scientist will tell you, the ability to do work. And work is just a measure of the energy transfer that occurs when an object is moved over a distance by a force. It's also when you add heat to something. Energy and work are actually defined in a circular argument by one another. Energy is the ability to do work, and work is done when energy is transferred from one body to another. This is deceptively simple, however, because energy is also what you're made of. Einstein discovered the famous principle of matter-energy equivalence, and you are made of matter, which is in turn made of energy, according to Einstein. But to fully understand energy, you have to begin at the beginning. And at the beginning, an infinitesimal moment after the start of the universe, there was only energy. The first configuration of the universe was entirely potential, pure energy, which almost immediately arranged itself into elementary particles. Now, these particles had no solid surface when they were formed, and they have none now. They were initially and are now composed entirely of energy, folded back on itself in a harmonic resonant function, which can be defined in terms of a wave equation a la Schrödinger. Those arrangements of energy are called atoms and molecules and elementary particles, but in reality they are just arranged energy, supercompressed energy, an unimaginably large amount of energy in an unimaginably small structure. Now these arrangements, these little wave packets of matter moving through the hyper-energetic soup at the beginning eventually began to congeal into bodies due to the action of gravity and electromagnetic force. Now, normally, electromagnetic repulsion kept them from touching one another, but when the atoms congregated in bodies of a certain size, gravity forced them together and compressed some of them into nuclear fusion. Now, remember that like charges repel one another, so this takes a lot of energy. It is a lot of work. Fusion is when two atoms of hydrogen, two protons with a positive charge, are forced to fuse with one another. They don't want to. This takes an enormous amount of heat and pressure, a huge amount of energy, and an awful lot of work to produce one atom of helium and a massive amount of energy output. Now, some of the mass of the two protons during this nuclear bonding is converted directly back into energy, and even a tiny bit of matter has a dizzying amount of energy in it. The particles radiate the energy produced by their converted mass, which is to say, they transfer energy by doing work on the surrounding body. This energy released from matter through nuclear fusion began to do work on the entire universe by adding energy via light, heat, and direct electromagnetic bombardment to nearby bodies. The universe is a furnace of sorts, constantly converting matter to energy to other forms and expanding outward at a speed that staggers the imagination. The scale of the objects we are talking about and the energy they output makes the idea of an energy crisis similar to the idea of one starving in the middle of a fully stocked pantry because they refuse to cook. If you understand the ubiquity of energy in the universe, the idea of scarcity seems laughable. The star, at the center of our solar system, radiates an amazing amount of energy, for example, which, if expressed in practical terms, would make you rethink your entire view of life. How much energy is being radiated by the sun in practical terms, then? To really understand the answer to that question, one needs to know how to measure energy in a way that one can relate to the real world. The easiest, most practical way to do that is to relate it to money. How much energy does the sun produce in dollars? Well, first, we have to express the sun's output. So in measuring distance, we use kilometers or miles as units, and in measuring electric power, we use watts. Watts can be seen as the amount of work essentially done by electrical energy transfer. You pay for electricity in kilowatt hours, so that's the unit of energy cost. Now, this is the measure of the amount of work you use electricity to do. It is work to heat water. It is work to light a bulb. It is work to turn the compressor on your air conditioner and refrigerator. You're moving stuff and heating stuff, and that is done by transferring energy from a generator to your appliances via electrical motion. So a 60-watt incandescent bulb uses 60 watts of energy. You're billed for energy in kilowatt hours, which is 1,000 watts continuously for 1 hour. So a 60-watt bulb uses 60 watt-hours or 0.06 kilowatt-hours of energy for each hour it's on. In California, the average rate for electricity is 31 cents per kilowatt hour, meaning that running a 100-watt light bulb for 8 hours would cost you about a quarter, or 25 cents. That means that if you run 10 100-watt light bulbs all day, it will cost you $2.50. Not much daily, but it starts to add up when you consider that your microwave is over 1,000 watts consumption, your dishwasher consumes between 1,200 to 2,400 watts, your stove between 1,000 watts and 3,000 watts, and your refrigerator probably an average of about 300 to 750 watts. So the total cost of the work you want done by light bulbs and appliances is therefore measured in total kilowatts for all of those items run together throughout the day. In 2021, the average annual electricity consumption for a U.S. residential utility customer was 10,632 kilowatt hours, an average of about 886 kilowatt hours per month, or between 29 and 30 kilowatt hours per day. That means that the average American pays about $3,300 to power their home over the course of the year. So to put this in perspective, the sun is radiating 173,000 terawatts just on the Earth at any given moment. The sun is radiating 173,000 trillion watts at any given moment just on the Earth. Now, if you imagine running an appliance which used 173,000 trillion watts at any given moment at California rates, you end up paying, for a day of that amount of power, just for consumption, 1,287 trillion, $120 billion. So at current rates, the sun is putting out $1.3 quadrillion worth of energy every day just to the Earth. Now let's say we could catch and collect 10% of that. Imagine adding $128,712 billion in energy value to the daily market just by collecting something falling from the sky. Does that sound like an energy crisis to you? It sounds like a crisis, but not an energy crisis. It sounds like an imagination crisis. $1 quadrillion of energy is falling from the sky every day, and we are worried about the price of a gallon of gasoline?